right, let's get amped up. We're almost done. So thanks for coming. Today we're going to talk about how to get your insecure Postgres passwords to SCRAM. Because if you're not using SCRAM, I bet you your passwords are insecure. Did you know that? Well, let's find out. The other way I like to call this talk is it's a tale of two hippos. Because we're going to see these two hippos kind of playing around, trying to get each other's passwords. But because it's Postgres, we also need an elephant. And there's going to be a guest star at some point in the form of a blue elephant. So let's keep all this in mind. We'll come back to this later. Just to do some formalities, a little bit about myself. I'm the VP of Platform Engineering at Crunchy Data. Focus on deploying Postgres to a variety of platforms like Kubernetes, Cloud Foundry, and so on and so forth. I've been active in the Postgres community for a long time. I've been on various governance and committees and a lot of those kinds of things. Actually, event organization, once upon a time, helping to organize an event in this very hotel, much like what we're doing today. I'm at a company called Crunchy Data. All we do is open source Postgres. We do a lot of cool, fun technology stuff with Postgres, and we are hiring. But boilerplate aside, what are we doing today? We're talking about password management in Postgres. And the goal is to understand what is the preferred way to deal with passwords in Postgres. So we're going to talk about all the different mechanisms, and then with a focus on SCRAM. SCRAM has now become the default as of Postgres 14, which I know everyone in this room is already upgraded to, so you're probably already using it. But that said, we're going to do a deep dive into why this is the preferred technique, why it's important, and of course, if you've not upgraded yet, how you can upgrade to it. And that's where we'll go. So if this sounds interesting to you, let's begin. Let's log into Postgres, something we've probably done many times before. Or if you just are starting with Postgres, you've done this today. Typically what happens, let's say you're using PSQL, you do PSQL, my host, my application name. Well, what's your username? Katz, I type in the wrong password. Maybe I get authentication failed. But then ultimately, I type in the correct password, and it succeeds, right? It just works. But what just works? What happened? How do I know my password's valid? And this is a question sometimes we kind of take for granted, right? We log into websites every single day. We think everything's safe, everything's good, everything's great. But I've seen things where I've seen JavaScript files you can just freely download, and everyone's user account and passwords in there. So it's actually kind of good to question what is going on with my password. So how do passwords work in Postgres? Well, before version 10, which is scary, version 10 is now the oldest supported version of Postgres, but before version 10, there were two different methods of storing passwords. There was Plaintext and MD5. There's this thing called crypt. Crypt got deprecated very early on. I believe it was using the internal Linux crypt program. But really, it was either Plaintext or MD5. And again, it's good to look at a little bit of the history in terms of what's going on, because chances are, if you're using a legacy Postgres system, you probably have this in some way, shape, or form, or you might be using this. So we're going to have some helpers. We're going to have some Hippos. Our Hippos are going to be our clients. And we're going to have some servers, which, being Postgres, they're going to be elephants. So some user personas. I do a lot of product work now, so I'm all about the user personas. And one of them is Gray Hippo. Gray Hippo loves Postgres. Gray Hippo's been using Postgres a long time, loves storing data, and because tends to work with larger data sets, Gray Hippo's password is data lake. We also have Red Hippo. Red Hippo is a friend of Gray Hippo and also loves Postgres, but Red Hippo is a little mischievous. Red Hippo wants to, likes to play around with Gray Hippo and kind of wants to be Gray Hippo. So we got to watch out for Red Hippo. Red Hippo might be doing some nefarious things. Maybe not in a bad way, but Red Hippo is a little mischievous. So first, let's look at the plaintext method. They're stored in plain text. So if your password's data lake, literally inside Postgres, your password is stored as data lake. It's also communicated in plain text. So there's nothing, there's nothing that might be protecting the password in terms of encryption. Everything's plain. This was the original method that was in Postgres. It was kept around while the Postgres drivers were updating to using the MD5 method, which we'll talk about shortly. It was actually dropped in Postgres version 10, where you couldn't use the plaintext method of authenticating passwords. Asterisk. There are some other authentication methods in Postgres that do use plaintext passwords, including LDAP, which is why my friend and colleague Stephen Frost will say that if you're using something like Active Directory, don't use LDAP to connect to it, use the GSS API, which will allow you to connect in a secure way. So how does this authentication flow work? I'll kind of skip through this because, or I'll speed through it because it's fairly straightforward. It's, hi, my name's GreyHippo, I want to authenticate. Postgres says, great, tell me your password. GreyHippo says, my password is data lake. Postgres says, confirmed, this matches, it's data lake, you can access your data. So of course, like everything's well, you've authenticated, everything's good, everything's great, but we know it's not, because this is susceptible to eavesdropping. Basically, let's say Red Hippo's listening in, Red Hippo's like capturing network traffic, sees GreyHippo, says my password's data lake. Red Hippo comes like, hey, I'm GreyHippo, wink, wink. Postgres goes through the authentication protocol and says, all right, tell me your password. Red Hippo says, yep, it's data lake. Postgres says, yep, you're definitely GreyHippo, you can log in. So yeah, like Red Hippo is now in the database as GreyHippo and has whatever privileges and data or whatnot that GreyHippo has. But sure, there's a way we can actually handle this. This is TLS. TLS, transport layer security, is the newer form of secure socket layers. Postgres refers to everything as SSL within the configuration parameters, within the documentation, but it's actually using TLS. And you can actually enforce a TLS level minimum, I think starting with Postgres version 13. That said, whenever you see SSL in the Postgres docs or configuration, it's using TLS. Like SSL v3 was dropped a long time ago. So the idea is that you perform a secure handshake, and once that handshake is done, everything's encrypted. So if you're trying to eavesdrop, you can't, you're not able to get that data. There's certain, I'll let you read this. There's certain ways you can enforce it. You can make sure all your connections are over TLS. You can even provide some strong guarantees on the client side to prevent man in the middle, or as I like to say, hippo in the middle attacks, or elephant in the middle attacks. And there's also ways you can actually really enforce TLS on the server side, starting with Postgres 12. I'll talk about that a little bit later. But the idea with TLS is that essentially puts a wall between Red Hippo and GreyHippo. Red Hippo can't eavesdrop the password anymore. So it seems like plaintext would work, right? There's no reason to have dropped it in Postgres 12. But Red Hippo is clever. Red Hippo says like, hey, can you give me a dump of the entire database? I'm doing work on my local environment. Let me like debug something. And GreyHippo's like, okay, cool, like I can do that. PG dump all, here's your data, restore it. So let's inspect the file, because basically what PG dump all does is that it's a logical copy of your database. It needs to be able to recreate everything that was existing in your database at the time you read the PG dump all, and that includes user accounts. And if you inspect it, you see that to recreate the GreyHippo account, there is a password. There's a plaintext password right there as you recreate that account. So even though we encrypted all of our connections, we still have a way to get the password. And it took a little bit of social engineering, but suddenly Red Hippo, again, has gotten GreyHippo's password and can log in. So we see that there's some things we need to do to tighten up password management, and this is where MD5 came in. Now, when we say MD5 authentication, we mean Postgres MD5 authentication, and there's actually a protocol to it. The first thing is how you hash the password, and the password hash is basically you take your plaintext password, you append your username to it, the username acts as a salt, and then you prepend MD5 to it. And if you look inside the PG_authID table, this is exactly how you see the password stored. The way that you do a verification is using what we call the Postgres MD5 protocol, which, as I mentioned, all of the client drivers, when this was added, all of the client drivers had to update to be able to support this as part of the Postgres protocol. The way it works is that it's like GreyHippo wants to authenticate. It says like, hey, I'm GreyHippo. Postgres comes back and says, all right, GreyHippo, we're going to use the MD5 method for authentication. Here's 4 random bytes. In this case, I used R4ND. So what happens is first that GreyHippo is going to generate what you would expect to exist on the Postgres server side, which is that MD5 hash of password plus username, and then prepend MD5 to it. Then as part of the authentication workflow, it adds that, that 4-byte nonce to it, takes an MD5 hash of that, prepends MD5 to it, and puts that all together, and sends that back to the server. Now, why does this work? Keep in mind, if you have a valid password, Postgres has that original MD5 hash stored, so all Postgres has to do is essentially calculate that and see if it matches what's being sent over by the client. And if it does, Postgres says, confirmed, you are definitely gray Hippo, you can get in. Now, is Red Hippo out of luck here? Because if Red Hippo hears this going over the wire, and keep in mind, when I say this, the hash of, the password hash plus that nonce, and Red Hippo tries to go through that workflow, Red Hippo is going to generate an incorrect hash, and Postgres is going to detect that and say, no. And Red Hippo is going to be like, oh, OK, this stinks. I can't get in. So we should be good now. But what happens if Red Hippo gets a dump of the database? So we do that. And again, remember, when we get a dump of the entire database, we need to be able to recreate all of the objects that we had to be able to perform all the Postgres operations. And in there is the MD5 hash of the password. What if I tell you that if you have this, you have their password? It doesn't matter if you don't know what the plaintext password is. If you have this, you have the user's password. Because even if maybe you're not able to log in via the PSQL prompt, but sure, like write something that speaks the Postgres protocol, get your random nonce. It's like, well, I already have the hash of the password and username together. I just have to attach that nonce to it. I get my new MD5 hash. I send it over the wire. And Postgres is like, oh, you are obviously gray Hippo. You can log in. And like this is funny because like Red Hippo's now like great. Like as long as like I keep getting like my PG dump all commands, I can always become gray Hippo. So this method was definitely better than just plain text because it created like a little bit extra friction, but like not too much. If you really want to get someone's password and get into their Postgres database, you could do that. But wait, there's more. There's more ways that you can get the password. Let's say you're creating a new user account and you do create role password data lake. Guess what? That plaintext password is getting logged into your server logs. So if anyone can access them, then they have the password. But you're like, oh, but I protect my server logs. I keep them behind all these things. But do you? What if you use a tool like a log analysis tool like PG Badger to analyze all the logs? Well, then maybe you've given someone the logs and there's password changes in them. They have the passwords. There's definitely ways around this. If you're using PSQL, use \password to change your password. That will prehash the password. So if it's sent over the wire, it's prehashed. Or you can manually prehash it. You can actually, as you saw back here, that's a valid command. You can take the prehashed password and use that to store it within Postgres. But keep in mind, even if you do that with MD5, I argue it is effectively useless because that is the password. So it's just like in the MD5 protocol, it's just slightly better. And if you have enough privileges, you can just get the password from PGAuth ID, which is the catalog view that shows user account information, passwords, and certain privileges. It does require you to be a privileged user, but if you're a privileged user, you can then like pretend to be other users or pretend to be other privileged users. Yeah, that's how I feel about it. These methods need to scram, play on words, but they really do. So what is SCRAM? And why am I such a big fan of SCRAM? SCRAM is the Salted Challenge Response Authentication Mechanism. Say that 10 times fast. But really what SCRAM is that it's a standard. It's an RFC. And as we know in Postgres, we love standards. We're open source. Not only open source, but like we love to follow the SQL standard. Whenever we implement something, we try to follow the standard. So there's a standard here. It's derived from a bunch of other RFCs. I won't read them all. But technically what we do in Postgres is we implement the 7767 standard, which is exactly the same as 5802. The difference is that 5802 says use SHA-1 as your hashing algorithm. The newer one says use SHA-256, or it specifies how you can use it with some of the larger SHAs. One of the nice things about SCRAM is that it's designed to be easy to implement. And you'll see that there's definitely like some certain steps in it. It can feel a little complicated, but if you look at it and compare it to other authentication protocols out there, it is relatively easy to implement. And the idea is that a lot of these layers exist. The other thing too is that what's nice about SCRAM is like this is a general purpose method. Like this is not specific to Postgres. Based upon how you're doing authentication in your applications or your products that you're giving away, you might want to implement this as well. It adds another layer of security for password verification. What makes SCRAM special is that it allows two parties to verify that each party knows a secret without ever exchanging the secret. So let me repeat that again, because this is a really important point. Two parties can verify they know a secret, like a password, but they never have to send the secret to each other. When I first realized that, when looking at SCRAM, this was a mind-blowing moment. It's like, wow. So we can basically determine, we both know something without ever exchanging it. I always find that so cool. Whenever you can figure that out, and I think it's important. And one reason why I love doing this talk is that I'm going to tell you. First off, I'm convincing you to upgrade to SCRAM as soon as possible, and we'll go through all of that. But when you see the flow and you see really how there's a certain elegance to it, and really how you can do this verification, it's so cool because it's a very safe way to do password verification. So how do we do this in Postgres? First, what you need to do in Postgres is you need to build something called a SCRAM verifier. I think we might have changed the name internally for how it's called, and I may have forgotten to update my slides around that. But you will see this, in places it's called, this verifier, and it's composed of five components: what message digest you're using, the number of iterations to use the password hashing algorithm on, a randomized salt, something called a stored key, and a server key. So what are all of these things? Actually, before we go into all these things, one important part about building the SCRAM verifier is also securely transmitting it to the server. This prevents eavesdropping on it. We'll talk about why even if an eavesdropper grabs this, it's not as useful. But I'll get to that in a few slides. So the first part of this verifier is the digest, which in Postgres right now we only support one method, SCRAM SHA-256. This allows us to support more methods in the future, SCRAM SHA-384 or SCRAM SHA-512. Right now it's just 256. We added support for something called SCRAM SHA-256 Plus in Postgres 11. This is for channel binding. We'll talk about it a little bit later. But for now, it's the same thing every single time. Next is the number of iterations. So when you generate the password, we're basically when you're converting the plaintext password into the form that you're going to store ultimately on the server, we use I always get the name wrong, the password-based key derivation function 2, or PBKDF2. The number of iterations is the number of times that you're going to hash the password to get it into its computed form. Postgres defaults to 4096, but you can actually set this value on your own. When I was playing around trying to implement the SCRAM protocol, I think I was using 10,000, and you can plug in this verifier using 10,000 iterations to Postgres, and it just works. So that's pretty cool, and it gives some flexibility if Postgres ever changes the default to be more iterations to do so. You need a salt. Basically just cryptographically secure, randomly generated string. Postgres defaults it to 16 bytes. You can set it to an arbitrary length. Postgres ultimately wants it stored in a base64 representation. So to build the secret, with these three things, you can now start to build up the rest of the secret. There's these two things we need to build, something called a stored key and a server key. To do that, we first need to prepare the password for it, and the SCRAM RFC defines specific rules around this. You go through something called SASLPrep. Now, I'm not going to go through all these steps. The slides will be available for reference. But the idea is that you need to normalize the password to a particular form. But the RFC specifically states that SASLPrep is used for UTF-8 encoded strings. Postgres supports more than just UTF-8. Postgres supports as many encodings as I'm aware of. And basically what happens is Postgres does SASLPrep if you're using UTF-8 encoded strings. If not, it basically just passes it through. So SCRAM will work no matter what. So I guess like we kind of work within the standard, but with some flexibility. If you're using a data lake, guess what? It just falls right through because it's using standard ASCII characters. We then need to generate what I call the salted password, and this is similar to PBKDF2, popular password hashing algorithm. Again, I won't go through all of this, but effectively this is what Postgres does. And at the end of the day, you create this, and in base 64, the data lake password looks just like that with the salt that we had generated from the previous step. So all right, we create this, the salted password. Now we can build the rest of the SCRAM secret, or the SCRAM verifier, excuse me. The first thing we build is something called the stored key. And the stored key is the SHA-256 hash of the client key. OK, well, what's the client key? The client key is an HMAC using the salted password as the key and client key as the message. What? So I figured a diagram's a little bit more helpful and actually kind of recaps where we are at this point in terms of our password storage. So remember, we start with the plaintext password of data lake. We went through the PBKDF2 algorithm to get the salted hash password. So the client key and server key are going to be an important part of our verification process. And the server needs to be aware of at least what the stored key and the server key are in order to complete the actual SCRAM authentication. To get the client key, you create an HMAC message you're basically signing client key as the message, and you're using the salted hash password as the key to get it. And then you take a SHA-256 of the stored key. One of the questions is, well, why are we doing this? The short answer is this is what the algorithm states that you should do in the RFC. But the idea is that you're introducing enough cryptographic entropy, or entropy might be the wrong word, enough cryptographic steps that's going to be very hard to derive the password, at least in a reasonable amount of time. We'll also see why, why the store key is very useful when we go through the actual SCRAM algorithm. So the server key is actually similar to the client key. We take an HMAC of that salted hash password, but instead of signing the message of a client key, we're signing the message of server key. So with all those things, if you take all these steps, you've built the SCRAM verifier and have made it possible for Postgres to do SCRAM. Now, I don't expect any of you to do that in the real world. There's an easy button. You can use \password. So long as you set your encryption method, which is the parameter in Postgres, to SCRAM SHA-256, you can use \password, and then you're good. Several Postgres drivers also support being able to do this natively within the driver. libpq is one of them if you call the libpq a set password function. I know PG2, one of the Python drivers, is able to support this. And there's other drivers that might just delegate to the libpq facility. So hopefully you never have to manually build your own SCRAM verifier. I have manually built my own SCRAM verifier, but for a variety of reasons. But remember, what's cool is if you do that, if you do use these recommended methods, this is a valid way to set your Postgres password, and then you don't leak your password into the Postgres logs. Now, you leak that into your Postgres logs, but what is that? That is very difficult to figure out what the password is. And sure, you get the SCRAM verifier. Maybe you could brute force attack it. Maybe it's a weak password. You're able to use some dictionary lookups to get at it. But you have to do work. With the plaintext and MD5 methods, you have the password. It's free. You have carte blanche. So we've now made it very hard. And sure, we probably prefer for Red Hippo not to listen, right? You probably still want to send this over TLS. You probably want to put whatever other safeguards you have in place. But even if Red Hippo does get this, we've made Red Hippo's life way harder. Red Hippo can't derive the password as easily as before. So now, at some point, Red Hippo might have access to a quantum computer, but we probably have like other problems when that occurs. So we can, as they say, kick the can down the road a little bit. So now we've built up the ability to do SCRAM, but how do we actually verify a password? That really is the key in all this, because we want to make sure the protocol is sound to be able to securely verify the password. Remember, the beauty of this is at the end, we're going to see that we verified the password without ever exchanging the secret. The only time we ever exchanged the secret was when we initially set this. So let's start. So the first thing, so as I said, the general idea is that we need to verify the knowledge of the secret. We also want to try to prevent replay attacks. So one of the key things is that we're going to be using nonces and authentication messages and grabbing things from around the Postgres protocol to do the verification. These slides are going to start getting very thick. So Red Hippo is actually listening in and eavesdropping. We're not using TLS for whatever reason. Maybe we're in a trusted network, if those still exist. And Red Hippo is just there listening in. So let's begin. So this is what happens when a client's authenticating to Postgres. We're going to go through the exact authentication workflow. Gray Hippo comes in and says, "Hi, I want to authenticate. I'm Gray Hippo." Postgres says, "Great. Hi, Gray Hippo. We're going to use the SASL method." So internally, Postgres refers to this as the SASL method. And it says, here's some available methods you can choose. Scramshot 256. If you enable channel binding, you might also have the option to do Scramshot 256 plus. Again, we'll talk about channel binding in a little bit. But basically, the client has a choice in terms of which authentication method to choose. So we only have one option here. So Gray Hippo is going to say, great, we're going to scram. I'm going to generate what I call a client nonce. It's just some cryptographically random bytes. Could be arbitrary length, but here's my one-time nonce. We send that up, we send that up to Postgres. Postgres is like, cool, all right, so here's my nonce. I'm going to generate a server nonce, and I'm going to append it to your nonce. So that way, we each have like something that we generated one time just for the scram session. And now we know like if any funny business is going on, because like I know my nonce, you know your nonce. If we don't like what we see, we can just bail. So I'm going to send you some information as well for you to try to derive the secret. Because remember, we're not sending the password up in any recognizable form. We need to be able to create proof that each side knows the password. So the Postgres is going to give some hints. Because like we can't just do this blind. We got to give some hints. So Postgres is going to send over the number of iterations you need to compute that salted hash password we talked about before. It's also going to send over the salt, because even with the salt, like there's not much you can do, but you need the salt to begin doing the the generation process. And now Postgres is going to send a challenge. It's like, all right, Gray Hippo, prove that it's you. I've given you the information for you to show me that you know the secret. Show me. And this is the really cool part, in my opinion. So the way that we're going to need to build up a proof. Yeah, it's almost mathematical, but it's going to, you're going to see how we build it up and then how we're able to prove we know the secret. So there's no getting out of doing the generating that salted hash password using the PGConf method. We have to do that. But remember, once we have that, we can start creating those cryptographic structures we made before. So we know that we need to iterate through the algorithm 4,096 times. We know what the salt is. So let's generate the salted hash password. So we're assuming the password's data lake. We're going to go through that. We're going to come up with that computed value, whatever it may look like. Here's the basic C4 representation. Before we proceed, recall we generated something called a client key before. And the client key was an HMAC on a message of client, literally the string client key, exactly like that, with the salted hash password. And recall that the stored key that we ultimately saved in Postgres was a SHA-256 sum of that client key. Now, one could say, we could pause right here and say, oh, all we're doing is generating that stored key and sending up to Postgres, and then Postgres is going to verify and say we're done? No. Because if we did that, we're no better than any of the other methods that we said. Because if you just are sending up that stored key, again, that's effectively the password. And that's not the case here. We're going to be sneaky. We're going to do something very tricky here. First thing is we know we can derive the client key. Because the client key, again, is just following that method. As long as I have that sorted hash password, I can get the client key, I can get the server key, I can get the stored key. So we get the client key. And from the client key, it's one step more to the stored key. Now, we know that Postgres and that SCRAM verifier does have that stored key saved on the server. But what we're going to do is we're going to create something called a client signature. And the client signature is we take an HMAC of some information that we're going to find in what's called the authentication message, and use the stored key as the signing element to create this client signature. It effectively looks like this. Now, authentication message is a little complicated in the sense that I can't fit it on one slide in terms of what it is. But it's essentially it's a bunch of one-time information that you have during this session you're trying to authenticate. And from there, you get this thing called, we're calling it the client signature. We then are going to generate something called the client proof. The client proof is an XOR between the client key and the client signature. And what we do from there is we put it into like a base64 format, and we take that that nonce we had generated in the beginning, and we send that up to Postgres. So what we're ultimately sending up is the client proof and the nonce to make sure that we're still in the same session. So we're going to remember what that client proof is, because this is the step where we can now verify the client knows the password. So Postgres gets that proof and says, all right, I know I can compute the client signature because I have the stored key. And remember, the client signature is the stored key. Some of the one-time information that that we're using as part of this session. I take the HMAC, we get the client signature. So all right, so I derive the client signature. And I can get what you think the client key is by doing an XOR against the client proof. Because when you XOR something, recall from, well, I guess I learned this in Intro to Computer Architecture. You XOR the same value back to the two values that XOR together. You get the other value. So I can derive what you think the client key is from taking that signature and doing that. And remember, the stored key is the SHA-256 sum of the client key. So if I take the SHA-256 sum of the client key and then compare it against what I have, that's the stored key, and compare it against what I have saved, I will know if you know the password. So that's pretty cool, because with this proof and being able to do some of this, these derivations, you can basically verify that the client knows the password. Because if that doesn't match, then, sorry, before I go ahead, if that doesn't match, then the client doesn't know the password, and you can say like, hey, that's wrong. Whatever you sent me, like, I don't know what you're sending, but you don't know the password. So that's cool. So at this point, we now know that the client knows the password. But the thing is, we've only proved that the client knows the password. We haven't proven that the server knows the password. That's that's interesting, right? Because we looked at all these other password methods, the MD5 and the Plaintext one. And we're always challenging the client and saying, like, client, do you know the password? But remember, there's two parties here. Like, the client, how does the client know it's connecting to a server that actually knows its password? Or how the server isn't just saying, like, oh yeah, I know the password, wink, wink, start sending me information. This is the cool thing about SCRAM. Both parties need to verify that they know the password. So the server is going to generate something called a server signature. And the server signature is similar to the client's signature, except it uses the server key. Recall that when we built the SCRAM verifier, we also stored something called the server key, which is just it's just the HMAC of the hash password with the literal string server key, and that's that. So we generate the server signature similar to how we generated the client signature, except using the server key. We have that one-time authentication info in there. We build out the HMAC. We send over the server signature to the client. Now, technically, at this point, Gray Hippos authenticated. Postgres basically says, you're good enough to be authenticated. But a smart client is going to go through this next step to make sure it trusts the server. Now, libpq does this by default, and the connection driver should do this by default. I can tell you that when I was reviewing the SCRAM implementation on one driver, they didn't go through this step. And I was like, hey, you got to do this step because you need to verify that the server actually does know the password and is not just telling this to you. Because even though their session is authenticated, you need to go through this additional step. Fortunately, this additional step is for the client is very similar to what the server did. You can generate, if you have the salted hash password, you can generate the server key. And if you have the server key, then you can basically generate the signature that was sent over. And if the signature you generate matches the signature that was sent over, then the server must know the password. And then you can say, OK, both parties know it. And what's so cool about this is we never exchange the secret at all. This is cool. This is a really cool method. And this is also why I try to emphasize this is a general purpose authentication method. You can use this in your own applications. Here's all that we transmitted. We transmitted, during the process, at the beginning, we transmitted the stored key and the server key. But, the way we did this is that we put it into, this, encrypted, well, not encrypted, this hashed, cryptographically secure method. We submitted, some nonces, one-time things, and information about the authorization headers. So even if Red Hippos listening this entire time, Red Hippos coming away confused. Red Hippos like, what just happened? Like, I can't figure out what's going on. Like, maybe I can capture all this traffic and try to brute force it later, but like, I have no idea of like, what secret was transmitted. So I think we've gotten Red Hippo stuck. But there's another element we need to consider here. And I intimated about it a little bit earlier, but we're stopping the rogue client, but what about a rogue server? First case, a server claims to know the secret. Remember, as I said on that last step, Postgres says like, hey, you're authenticated. So even though you receive the server signature, technically the client can start running queries against the Postgres server with that level of privilege. And if the client doesn't actually verify that the server really knows its password, it can start like sending like secret information over. And then the server is like, well, fine, like, really, you trust me? Okay, thank you. Like, you gave me all your secret data. I'm going to now go sell this and buy tasty fruits and vegetables, because I presume that's what elephants eat. So you actually need to do that verification step. This is more important if you're implementing a driver or writing this protocol on your own, but rest assured, this is something that libpq handles. There's also the elephant in the middle attack. Recall that we can use TLS to secure endpoints. I strongly recommend use TLS to secure endpoints. Maybe my next talk will be about just Postgres and TLS. It's certainly a deep topic. So how can we ensure that even though we've used TLS to connect, how can we ensure that we're connected to the endpoint that we want to be connected to? So even though we go through this step, potentially a rogue server can come in and say, all right, I know, even though you did this handshake, are you sure that you've connected to the server that you're intending to connect to? And this is possible even because we haven't exchanged any information about the TLS during the SCRAM protocol. But basically, we haven't like mapped anything to that level. So it is possible for an elephant to get in the middle. But there's a few ways to avoid this. The principal one around SCRAM itself is channel binding. This is discussed in the SCRAM RFC, and this was introduced in Postgres 11 to basically ensure that when you do the TLS handshake, you're still talking to the server that you originally believed that you were talking to. And particularly for the client, it's I am sure that I'm working with the Postgres server that I want to. This actually was somewhat, how to say, Postgres 13 made this much more useful because really this is to protect the client, primarily in the Postgres space. And the client could not actually enforce channel binding until Postgres 13. Basically saying that channel binding is required. If you don't advertise channel binding or allow me to do channel binding or force me to a downgrade attack, then there was no way to bail. So Postgres 13 introduced the ability to say, like, I'm requiring channel binding. Now, my humble opinion about this, I don't know, I'll talk a little bit about this towards the end. I want to make sure I have enough time to cover this concept. This checks that you're connecting to a valid endpoint, but it doesn't check that you're connecting to a valid identity. What do I mean by this? Basically, channel binding ensures that the endpoint you connect to, let's say it's a server like Jonathan.Katz server on the internet. It says like, okay, you're still connected to this server, but it doesn't check against a trusted CA or a certificate authority you choose to trust that I actually am that Jonathan Katz server. It might, I'm just claiming to be that, and like, sure, you're still connected to me, but like, I might not actually be the server that you're expecting to connect to. The way you get around that is using SSL mode equals verify full, which if you're using TLS and you really care about trust, you need to be using that in your environment. Again, see my next talk on Postgres and TLS. But at least, like, if you require channel binding, basically what you do is you get some of the additional TLS information into the SCRAM authentication protocol. It basically allows you to continue doing SCRAM knowing that you're actually talking to the endpoint that you expect to be talking to. I mean, also like with the way Postgres works, the way the Postgres connection works, it's not as a big deal because like you are like within the same connection space. But if you're going over a proxy, then there's some things you may want to consider. Which leads us into probably a longer topic, which I really wish I made some slides on. It's in terms of doing SCRAM with a proxy, like PG Bouncer or PG Pool. That is an interesting topic in itself. If we have a little bit of time left, I will talk about it. Now, I hopefully, in addition to providing what I hope is an informative talk about how SCRAM works, I've hopefully, if you have not updated all of your servers to SCRAM or want to, well, let me put it this way. Hopefully I've scared you into updating everything to SCRAM. But that said, how do you actually do it? First, you need to ensure that your driver supports SCRAM. And the good news is that effectively every single Postgres driver supports SCRAM at this point. Even better, like I said, currently the oldest supported version of Postgres now is Postgres 10. So all of these supported versions of Postgres support SCRAM. And Postgres 14 further incentivizes this because the default password method now in 14 is SCRAM. So the first thing I do to upgrade is you need to set the password encryption parameter to SCRAM SHA-256. You can still keep MD5 as the authentication method in the HBA file. We did something within the code base that basically first checks to see if, even if MD5 set there, we first check to see what does the password field in the PG auth table look like. If it looks like a SCRAM verifier, it says like, okay, don't do MD5, do SCRAM. If it looks like MD5, it goes ahead and does MD5. And like the reason is that to allow people to upgrade. You can then have, anyway, once that's all set up, have your users rehash their passwords. They can start SCRAMing. And when everyone has now updated their passwords to the SCRAM verifier, you can switch it back to SCRAM SHA-256. And like I said, pretty much all the drivers support this now, so there's really no excuse not to upgrade. I know there, of course, are complications in the real world around that, but if you're using software that's still not using SCRAM against your database, talk to your vendor and get them to upgrade. So, in conclusion, this basically, the way this talk started was asking a simple question like, we logged into a Postgres database and it just worked, and it was asking about like, what just worked? And this is important, like not all password methods are the same. Questioning like, it just works does lead to better solutions. And it's fortunately, we did adopt the SCRAM protocol in Postgres, and I think, it's a very good solution. I think it lasts a very long time. Maybe something better comes in the future, and perhaps we adopt it. But the decision was made to go with this because it's standard, it works, it's proven, it's safe, and people are continuing to work on it. SCRAM is a general purpose solution. I have some examples for how to do it, and you 100% should upgrade your passwords. And a fun note, I only briefly talked about it, but there's a way to do two-factor authentication in Postgres starting with version 12. In the HBA file, if you set client cert to equals verify full and combine it to SCRAM, Postgres is a good check that your client has both a valid TLS certificate that it can match to your identity, as well as doing SCRAM authentication. So with that, I say thank you. Thank you to my lovely illustrated helpers. Thank you to our graphic designer at Crunchy Data, Samantha Wheatley, for designing those a few years back. They've withstood the test of time. And thank you for coming. And if you want to hear me talk about the fun of dealing with connection proxies, I'm happy to do that. But first, I will pause and provide some time for questions.
Hi. So my boss told me I need to make Postgres capable of doing password complexity tests for compliance purposes. And how do I do that if the clients make their own verifiers?
Yeah, so that's a very good question. So I think I might know your boss. But that said, so there's a few ways that we could do this. There's certainly many password complexity verifiers that are out there. I've used ZXC VBN in some client applications, but the problem is that as you're trying to get at is that this is a decentralized problem at this point because Postgres itself, for one thing, if we're sending this type of password up to Postgres, already in a hash form, Postgres can actually do any of the complexity checking. So the onus is on you to do that. Is there a better solution to it? Perhaps there's something we can do in libpq around password complexity checking as part of the algorithmic process. I'm sure that will lead to a great debate on the mailing list in terms of what is the right way to do that. And I don't know if there's any RFCs out there around the way to do generic password complexity checking. But currently, the onus would be on the client, or I guess the policy of what the client is implementing to do that. But it's perhaps like a very good topic to discuss. And if we were to do it, we'd have to be something in the client drivers in order to enforce that.
I may be wrong on this, so definitely check it. But I think NIST removed password complexity from their recommendations. So that could be fodder.
Yeah. So the 800, gosh, what is it, 883B? I can't even remember which standard it is. But they now recommend that you check against dictionaries rather than doing, upper, lower symbol, length, blah, 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 blah. So they have a different kind of complexity checking. It's still, it's not really complexity checking anymore. It's essentially dictionary attack strength checking. But
dictionary attack will only work against if you have hash.
Right, yeah. Well, that's what I was challenging him on. So, the right answer is either the client does it and we trust the client, boo, or you send the password to the server does it, and then the server stores it in the hashed format, and that gives you an opening when the client is setting the password, but, maybe that's acceptable, right? If the alternative is every password is A, perhaps, and the server can't check it, then perhaps you're a little bit better off, forcing the client to send the server the password one time. So, there's definitely trade-offs to be made, and of course, the bike shedding on the list would, I'm sure bring all of that out. But, it's an interesting thing that we kind of need to talk about, right, at some point.
Yeah. Maybe there's a hook we could create to do this.
What?
Maybe there's a hook we can create to do this.
A hook?
A hook. Maybe, I don't know.
For what it's worth, in the Windows world, when you have a password policy, you do have to send it to the Active Directory server, right? Even though the server will end up storing it hashed with the nonce and everything. So you can still do challenge authentication after that, but the initial setting does require, because compliance is more important than security, of course.
You gotta check those boxes.
I thought for those cases we were recommending people use LDAP that has the the checking inside of it, but the problem is you've lost all this security because that password's going to have to go to the server, then to LDAP, and then back again every time somebody logs in, and that's a pretty serious problem.
But you can use. I was gonna say you could use GSS API. If you're using Active Directory, you could use Kerberos.
Right. That's another. Yeah. So something. The idea is not necessarily to do with the client, but to use a central authentication. But then you have to always use that central authentication. You can't just use it to set the password and then start using SCRAM. That's the problem.
could you maybe go, I don't know how much time remains for this, but could you maybe go over the security model of like, in general, what it looks like when you have PG Bouncer in the mix using SCRAM?
Sure. I should have made a slide for it. So yeah, so PG Bouncer added support for SCRAM. I think it was 1.13 and improved upon it in 1.15. So I will try to act it out like this. So let's say here I am, I'm the client. Client says I want to connect to Postgres. PG Bouncer connects to PG Bouncer. PG Bouncer is like, all right, we're going to do SCRAM. The way you should set up PG Bouncer is to reach into Postgres and grab the SCRAM verifier. So basically what happens is that the client and PG Bouncer do SCRAM. Let's say everything is valid. So recall that the way we're able to do SCRAM, we're able at a certain point, when you get the client signature, when you get the client proof sent over to PG Bouncer is able to get the stored key from that because PG Bouncer is able to get the client key. Once PG Bouncer has the client key, then it's able to authenticate to Postgres. Why is that? Because the client key is the HMAC of the salted hash password. And effectively, the client key is used to get the stored key. But we need the client key in order to generate the client proof. So as soon as PG Bouncer has the client key, and if it's a valid client key, it can act on behalf of the user that was connecting to it. So then PG Bouncer can go to Postgres and do in SCRAM with Postgres, but PG Bouncer doesn't need to generate the salted hash password. It has the client key already from that, can act on behalf of the client and then connect. So all that's good and great. The issue is currently we don't do this within the allowance of the SCRAM protocol. So the SCRAM protocol actually defines a way the accounts for using proxies. There's a parameter that you set that says you can act on behalf of the user that's connecting to the different endpoint. And I'm not recalling off the top of my head of the exact way for doing that, but the next step in Postgres, if we need to fully implement SCRAM, is to be able to allow for that type of connection to go through. Now, basically at this point, what you have to do is you have to trust PG Bouncer is doing the right thing, or your PG Bouncer is doing the right thing, and not like acting on behalf of a user, in a way that might be nefarious. But in general, if you're using a connection pooler, you're already placing that trust in said pooler. So actually, I would say the way PG Bouncer does it is very clever, and it allows a way to do it I'd say in a mostly secure way. Would the one step better make it that much better? I'd have to look closely at it again. But it would be good if in the end in Postgres, we do support the official SCRAM way of being able to allow for a proxy authentication method. Because basically what's happening is that PG Bouncer can essentially assume the identity of the Postgres server in this regard, and then with channel binding, that basically makes it the way channel binding works, that makes it not necessarily work because the end channel is the Postgres server, not PG Bouncer, but yet you're binding to that PG Bouncer trying to act on behalf of you in the actual endpoint. This is why I promote, if you really want a secure channel, use SSL mode verify full on all your different TLS connections, which again, I will do that in the next talk. If it gets accepted to a conference, of course. Does that answer your question? Does that make sense? I know I went through it kind of quickly. I have a blog about it if you search for my name and PG Bouncer and SCRAM.
Yeah, maybe just sort of a not totally related follow-up, but are there any trade-offs that you have to accept with PG Bouncer pooling modes or supporting operations, or maybe when you have maybe multiple users, are there any complexities there?
Well, this gets very loaded. So in terms of SCRAM itself, no. The connection's a connection. The trade-offs with the PG Bouncer pooling modes are the trade-offs you're taking anyway with the PG Bouncer pooling modes, but it's not within the authentication model. Now, you want to be careful which users you allow your PG Bouncer to act on behalf as. So the constant debate I get into is I have people who they want to connect as a super user to Postgres via PG Bouncer, and I always say you don't want to do that because, let's say you have a lockdown PG Bouncer account that's acting on behalf of you to do the impersonation. Well, if you're allowing them that lockdown account to act on behalf of a super user, you've made that account itself a super user. And so effectively, I say effectively anyone can become the super user then, connecting to PG Bouncer so long as they're able to, become that PG Bouncer user. So it's things like that you need to consider. yeah, that's my 2 cents on the topic.
All right, I think that's it.
Cool. Well, thank you.
Thank you,
Thanks
Jonathan.
for coming.